Welcome to Unit 8. Unit 8 is all about estimating area under a curve. This is definitely different than what we've been doing before, but it's kind of similar in that we are going to relearn a geometric way and then we're going to do the same thing using calculus in Unit 9. So right now we're going to stay in just geometry using either area or area of a rectangle or area of a trapezoid. This unit might be a bit confusing in that we're not learning a lot of calculus, but I've really tried to pare it down to exactly only the things that you need in order to be successful on the exam and not the extraneous information. Although the extraneous information is really good for understanding, we don't really have a lot of time this year to learn material that's not necessarily going to be assessed. In 5.2, we're going to talk about the definite integral. So in calculus, we have two pieces that we're going to learn this year, the derivative and the integral. Obviously, we've talked a lot about the derivative. Now we're going to talk about the integral. So in order for the definite integral, it's the exact same definition of what we've been talking about in 5.1. It's the area as the limit as n goes to infinity of the summation, which is the sum of all the areas of all the rectangles. And we're going to take that limit as the number of partitions go to infinity. So that means that we're going to have an infinite amount of rectangles underneath the curve. The assumptions that are being made is that the function is continuous on the interval, the function is non-negative on the closed interval, and the closed interval is partitioned into n subintervals. So same constrictions that we had before, but now we're just going to give it a new name. Next, we're going to talk about Riemann sums. This is a really important one. This is always on the test in lots of different ways, and this is what we're going to focus mostly on, is finding our Riemann sums. Riemann is he's a mathematician, and it's a specific way of finding these sums. It's very geometric, though. So in order to do the Riemann sums, notice it's the same idea. We have the summation as I goes from 1 to n of the y value, the height, times the width of each interval. It's important to notice here that the width is going to be the same for all the intervals in my Riemann sum. The function is defined in the closed interval. It's not necessarily continuous, and the length of the subintervals are not necessarily equal. So each one could have a different width. The number ui may be any number in the subinterval. The sums is the summation of the length, the height times the width, is called the Riemann sum for f on a to b. They form a foundation for integral calculus. So this is just super, super important. So we have three different types of Riemann sums: the left Riemann sum, the right Riemann sum, and the midpoint. The left is formed by using the left endpoints. The right is using right endpoints, and the midpoint is the midpoint of each. Pretty self-explanatory, but you'll see in practice how it really works. Let's see this example. I think it will make more sense. It says, example 1, for the function f of x equals x squared minus 3, partition the intervals into 4 subintervals, and then they give us the intervals, 0 to 1, 1 to 2, 2 to 4, and 4 to 6. Notice they are not the same length. And then form the Riemann sum for each. We're actually going to do the left and the right just so you can see the difference in doing them, and then we'll do the midpoint. But the first thing I want to do is make my XY table. A lot of times they don't make an XY table up and down, they make it horizontally instead. And that's just to save room. But where I need some more room, I'm going to do it this way. So let's see, they told us 0, 1, 2, 4, and 6 are the numbers I need. So I'm just plugging in, old school, making an XY table. So negative 3, negative 2, 1, and let's see, 36 minus 3, 33. Now to do my left Riemann sums, I'm going to use my left endpoints. So I use these numbers because they're on the left of all of my points. I will draw a picture of this that might be a little more helpful. But my first rectangle is going to be from 0 to 1, so it has a width of 1, and a height is going to be my left endpoint of -3. My next rectangle has a width of 1 and a height of -2. My next rectangle has a width of 2 and a height of 1. And my final rectangle has a width of 2 and a height of 13. Notice I have 5 numbers that I have written down here on my XY table, but I only use the first 4 when I'm making 4 intervals, 4 subintervals, and I use the first 4 when I'm making the left. We're going to use the last 4 when I'm making the right. So let's continue, and then I'll show you about the right. So we have -3 plus -2 plus 2 plus 26. So we're going to get 22. All right, let's take a look and do my right Riemann sum. So I'm going to redraw my XY table. 0, 1, 2, 4, and 6. And this time I'm really going to focus on my last 4 intervals. I still need to think about how wide this interval is, but instead this time I'm going to be taking the right endpoint. So I have, it's 1 by -2, and then this one is a 1, and the height is 1. This one's 2, and the height is 13. And this one's 2, and the height is 33. So notice again, we have excluded one of our endpoints. In the first case, when we used our left intervals, we excluded the last point, and when we're using our right, we exclude the first point. So either the first or the last always gets excluded. For the right, we start at we only take the last 4, and for the left, we take the first 4. Okay, so now let's do that. We get -2 plus 1 plus 26 plus 66. We get 91. So what this tells us is that our area is somewhere in between 22 and 91. That's a pretty wide range, but if you take a look at the picture in the book, it's a pretty funky looking function. So there's a lot of space that we're missing, either overestimating or underestimating. And okay, now let's take a look at our midpoint. So we're going to be using the same equation and the same intervals. So we'll make our XY table, but we need a little more space in there, so I think I'm actually going to make it horizontally. So for the midpoint of each, so these are my my blocks that I'm going to be using. Those are my intervals. Those are the intervals they told me to use, so those are the intervals obviously I have to use. But for the midpoint of each interval, I'm going to need to come up with these middle numbers. And in order to do that, I'm going to need a little bit more information. So the middle of 0 and 1 is 1/2. And now I'm going to plug 1/2 into my function of x squared minus 3. And I get -2.75. And then I'm going to look at the middle of 1 and 2 is 1.5. And I'm going to get -0.75. And the middle of 2 and 4 is 3. And my y value is 6. And the middle of 4 and 6 is 5. and my y value is 22. So these are the points that we're going to be using. Instead of the end points, we're using the middle points. So we're still looking at the width of our rectangle goes from 0 to 1, so my width is 1, but my height is 2.75 for this first rectangle. My second rectangle goes from 1 to 2, so my width is still 1, but my height is here at negative 0.75. For the third rectangle, I go from 2 to 4, so my width is still 2, but my height here is 6. For the last rectangle, I go from 2 to 6. My width is 2, but my height is 22 right here as my middle point. And then I'm going to plug all this into my calculator and find my area. 52.5. So that's a little bit better of an estimate. It's not nearly as wide of a range between 22 and 91, but notice that my 52.5 is in the middle of those. So it took a little bit of extra work, but it gives you a closer answer to the actual answer. This is a super important definition that we're going to come to now. The definite integral. It's basically everything we've spoken about before. We take the height and the width of all of our rectangles. We add them up. This is a new word here, the maximum. It's going to be the best estimate that we're going to get. We take the limit of that max as it goes to 0, and then we get the integral. This is a super important definition. You need to be able to go back and forth between these. They're really easy multiple choice questions on the AP test, so you just need to be able to go back and forth. And no, I understand that you don't really know what the integral means yet, but we're going to talk about that soon. But you just need to be able to go back and forth between these symbols. So what this says is the integral, that's what this symbol is, the integral, from a to b of the function f of x dx. Dx just tells us, just like dy dx, dx just tells us that the variable is x. So when the above limit exists, we call it integrable, which is just like differentiable, over a to b, or that the integral from a to b of the function f of x dx exists. This is really, really, really important, and it's kind of the cornerstone of everything we're going to do for the rest of the year. So just to highlight that this is exactly the same, we're going to approximate the integral from 1 to 9 of x minus 3 squared by partitioning 1 to 9 into 4 subintervals, each of length 2. So it's asking us to do the exact same thing that we had just done. So I'm going to make my xy table. Again, that you always see their xy tables this way and not vertically, just because it takes up less room. So we'll just keep working on that too. And I'm just going to fill in my table. They're telling me that my interval should have a length of 2. So let's see, we're going to start at 1, and then, so if I take 9 minus 1, I divide by 4, I get 8 over 4. So the width of each of my intervals is going to be 2. So my first one's 1, and then my next is 3, and my next is 5, and my next is 7, and my last is 9. So I go from 1 to 9 with 4 intervals, each of width 2. And now I'm going to find my y values for these. So 4, 0, 4, 16, and 36. Now let's find our left Riemann sum. So for my left Riemann sum, I'm going to use my numbers on my left intervals. So I use all of those. My width for this we know is my delta x is 2 for all of these. So from 1 to 3 I have a width of 2 and a height of 4 because I'm using the left hand point. From 3 to 5 I have a width of 2 and a height of 0 because I'm using the left hand point. From 5 to 7 I have a width of 2 and a height of 4. I'm using the left hand point. And from 7 to 9 I have a width of 2 and a height of 16. So let's just find the area for all of these. And I get my area is 48. All right, now we're going to do the same thing, but we're going to use the right-hand endpoints. I'm going to rewrite it just so we can have a little more clarity here. So same chart, I'm just going to be using the right-hand points instead of the left this time. So my rectangle from 1 to 3 has a height of 0, so a width of 2 and a height of 0. From 3 to 5, I have a width of 2 and a height of 4, because again, I'm using the right-hand point. From 5 to 7, I have a height of 2 and a width of 16, and then from 7 to 9, I have a height of 2 and a width of 36. Of course, you could always do 2, because 2 is in each one. I could factor the 2 out and do 0 plus 4 plus 16 plus 36, if that's easier for you. So 20 plus 36, we get 56, and then 56 times 2. That might be a little bit easier to do the computation, but it doesn't matter, you get the same answer. So I know that my area is going to be between 48 and 112. Now let's do the midpoint. Again, I'm going to leave myself a little bit more room for this one, because I'm going to need to find the midpoint of each of these intervals. So 1, 3, 5, 7, and 9. So the width of my intervals is still 2, but we're going to need to find those midpoint numbers. So the middle of 1 and 3 is 2, and my y value at 2 so it's going to be 1. The middle of 3 and 5 is 4, and my y value is also 1. The middle of 5 and 7 is 6, and my y value is 9. The middle of 7 and 9 is 8, and my y value is 25. So my intervals are here. These green blocks are the intervals that I'm using. So they still each have a width of 2, but now I'm going to be using these midpoint numbers of 1. My width is 2 for the next interval, and my midpoint number is also 1. My width is 2, but my midpoint number is 9 for this one. And my width is 2, and my midpoint number is 25. So again, midpoint causes a little bit more work, but not super hard. And I'm going to get 72. So I get an estimate in between 48 and 112, and it's a little bit closer to the exact estimate. So notice this is exactly the same thing we've been doing. The only difference is the form that they gave it to us in. So we just need to be able to understand what that's telling us to do. Now in the middle of 5.2, they kind of throw in some properties of integrals that we're not really ready to practice, but I'll just go over with you. If we have a constant from A to B, so if our endpoints are the same, that means the width of our rectangle is 0, because we're not going from one number to another, we're just staying at that one number, so that the integral, the area under the curve, is also 0. So if our endpoints are the same, we're 0. Here, if our endpoints flip, we're just the negative. So instead of going from A to B, if we went from B to A, it's the same area, just negative. On this slide, they're going to give us another definition or another property of integrals. So if we have a continuous function, then the definite integral goes from A to B if f of x exists. If the function is bound on the closed interval, it has at most finite number of discontinuities. Then the integral also exists. And then one more here. If the function is a constant, then the integral from f of x dx from a to b is the constant times the dx, which is the constant times the length of the integral. So this just means if I have a constant height, it's going to be the height times the width. Which is exactly what a rectangle is. And they ask us to just do a couple examples of this. So my height is 3 for this one, and my width is 3 minus 1, or 2, so 3 times 2. This integral is 6 because my rectangle has an area of 6. Here, my height is 1, even though the 1's not really written. So it's 6 minus 2. My width is 4, so 1 times 4 is 4. My integral is 4. The area of my rectangle is also 4. Here, my width is negative 2. And my height is negative 2, and my width is 4 minus a minus 3, or 7. So negative 14 is the area of my rectangle, which just means it's an area that has 14 and it's in the negative y area. So if I had something that looked like my rectangle would look like that, it would be in the negative y part, going from negative 3 to positive 4. Hopefully these examples help show that area and integrals are completely exactly the same. They're interchangeable words. So when I think about an area under the curve, I think about an integral. When I think about an integral, I think about the area under a curve. And for right now, we're keeping that area to rectangles. Let's look at example 8 on page 401. An object in rectilinear motion moves with the velocity v. Table 1 displays the velocity v in meters per second of an object for selected time t in seconds. Part A asks us to find the Riemann sum for v on the interval from 1 to 8. It doesn't specify if it wants a right or left Riemann sum, so we get to use our own judgment, whatever we want to do. I think I'm probably going to choose the right Riemann sum, but I don't think it matters whichever one you want to choose. So let's see. From 1 to 2.5, it's 1.5. And like I said, I'm going to choose I meant left. It doesn't matter, but I'm going to choose my left. So that's going to be times 6. And then from 2.5 to 3, that's 0.5, and times 0. And from 3 to 5 is 2 times negative 4. And from 5 to 8 is 3 times 2. I'm just going to put this in my calculator. And I'm going to get 7. So an estimate of my area is 7. Now I need to come up with the units. So my velocity is in meters per second, and my time is in seconds. So when I get that, it's meters. So this is 7 meters. So let's interpret what that means. It's the displacement of the object. So it's moved a total of, its net displacement is 7 meters. If you're thinking about this in terms of work in physics, its work would be 7 meters because the negative takes away and the positives add. So the net displacement is going to be 7 meters.